everyone. Welcome to a new episode, the 27th, in the series Mathematical Methods for Economics. In this video, we will cover some economic applications of the implicit differentiation technique, which I had introduced in the previous video. In this part of the video, which is the first part of the 27th lecture today, I will walk you through an application from microeconomics. And what you see is some very interesting results emerge with just some simple tools of demand and supply. But before we begin, let's do a quick recap of the method that is implicit differentiation. As I mentioned in my previous video, implicit differentiation is basically an application. It's nothing but an application of the chain rule. And it comes into application when we have to find a derivative, when we have to look at how one variable changes with respect to another in the following context. So let us understand what the method of implicit differentiation is all about. Let us assume we have two variables, x and y, which are related by an equation. Okay? And in this context, where there are two variables x and y which are related by an equation, we want to find dy by dx. So what we will do here is, we will first differentiate each side of the equation with respect to x, considering y as a function of x. And here typically you will be using the chain rule. Now, once you have finished differentiating each side of the equation with respect to x, then you can solve the resulting equation for dy by dx. So actually the method is quite simple, and if you want to know, if you haven't seen the previous video and you want to know more about what implicit differentiation, what this technique is all about, and you want to do some examples relating to this technique, you can go back to the previous video which introduced implicit differentiation. So what I was saying was that this is a pretty simple tool, but more importantly, this is a very useful tool for carrying out economic analysis. And for anyone training to be an economist, this is something that I had said earlier also, that for anyone who's training to be an economist, this is one technique that you must master. And for the purpose of your training, do pay attention to what we're going to do today. We'll go through these economic applications. So do listen in as we navigate through all of these economic applications. The first application that I'm going to look at today, the economic application, is from microeconomics, and here I'm going to look at how taxes, in our case we will be looking at a tax, a unit tax in particular, on the consumers of a good or the producers of a good, and we want to understand here how taxes affect market outcomes, how they affect the economy in general. And again, we'll be using some very simple tools here. But just to back up a little bit, just to give some background, you all would be knowing that taxes are a very important policy instrument used by the government to raise revenue for public projects such as defense, roads, schools, hospitals, and so on. So with this in mind, let us suppose you have the government imposing, let's say, a unit tax on the consumers of a good. And in this framework, we will also we'll try and address a related question, which is that of tax incidence, where we look at who bears the burden of the tax, how much of the tax, what proportion of the tax is borne by, what proportion of the burden is borne by the producer, and what proportion is borne by the consumer. Specifically, let us suppose the market for a particular commodity, and this is an example from the textbooks at Sater and Hammond. So the market for a particular commodity is given by the following linear demand and supply functions. So you have the demand function, which is given by A minus B times the price, and the supply function, which is given by alpha plus beta times the price. So we are taking linear demand and supply functions to keep things simple. The parameters here of the demand function are A and B, as you can see, and the parameters of the supply function are alpha and beta. We are going to assume here that A, B, alpha and beta are all positive. So, for example, note that given that we are assuming that B is positive, this would basically imply a downward sloping demand curve if you look at this function, because there is a negative sign in front of B. So, the coefficient of price here would be negative minus B, and we would have this would then indicate a negatively sloped demand curve. Similarly, since we are assuming that beta is positive, this is then going to give us an upward sloping supply curve that then takes care of the slopes of the demand and supply curves. Now, having said this, let us suppose, let us build things up a little bit with a tax, and let us suppose a tax of T per unit is imposed on consumers. So, basically what we are saying here is that for every unit of the good that the consumer buys, regardless of the price, the consumer has to pay a tax of T, which is in addition to the price that he pays for the good that he buys. Okay. So, that is to say that the price that the consumer will pay effectively is now going to be P plus T. Right. Now, here you can think of things in this way, that let us suppose the consumer goes to buy a commodity, and at the entry only he has to pay, so he has already decided that he is going to buy let us say so many units. So, for every unit that he buys, he has to give a tax of T to the to some agent of the government who is standing there. And this is to say that the the tax of T per unit will go to the agent of the government agent, and P is what he will be giving to the seller. So, P here would reflect the price received by the seller, price received by the producer, and effectively the price which the consumer will be paying will be P plus T. So, P he will give to the seller and T he will give to the government agent. So, effective price is P plus T, which in turn implies that the demand function now is going to be given by, if a tax of T per unit is imposed on consumers, it's the demand function is then D equal to A minus B times P plus T. However, the supply curve will not be affected, because here the tax is on the consumers and the producer's cost structure is not affected in any way. So, the supply curve remains as it is. Now, just wait, hold on a moment to see and understand a little bit what these equations, these new equations are leading us to. Now, if you notice here, and if you remember the stuff that we did on the shifting of graphs, and you can go back to my one of my earlier lectures on the shifting of graphs. If you notice here, we have this demand function D equal to A minus B times P plus T. Now, if you compare this with the original demand function without the tax, which is D equal to A minus B times price, basically with the P plus T now this is going to imply that the demand curve after tax would shift to the left exactly by the amount of the tax. Okay. So, this is how we have to see this demand function after tax, and what we are saying here is that there will the demand function will shift to the left, it will shift towards the origin by the full amount of the tax. And this can also be seen in another way from the point of view of economics. We can also think of this as a situation where, because a tax of T is levied on the consumer, the willingness to pay for the consumer, the willingness to pay, the consumer's willingness to pay to the producer will get reduced by the amount T. So, that is to say the demand curve shifts down, it shifts to the left, or equivalently it shifts down by the amount T. Now, I will show you a little video to illustrate what exactly is happening. Let me give you a graphical illustration of the impact of a per unit tax, a quick graphical illustration, and then we will go back to the math. Now, in this video, we have the demand curve is shown here as a downward sloping blue curve, and the red curve is a supply curve. You can see the equilibrium is the price is P star and the equilibrium quantity is Q star. Now with the tax, you can see that the demand curve shifts left, or you can equivalently think of it as shifting down by the full amount of the tax. And in this case, when it shifts down, the new equilibrium, if you see the video here, the new equilibrium is established where the price is now P sub S. So this represents the price that the seller is going to receive. This is a price at which the transaction will take place now with this new demand curve. So PS is the price received by the producer, and the price paid by the consumer will be given by PS plus T, because T is going to the government agent, as I told you in the beginning, and PC then represents the price paid by the consumer. So you can see here the tax is creating a wedge between the price received by the seller and the price paid by the consumer, as shown by this vertical distance. And this area that is shaded in pink here, this represents the total tax revenue that the government will receive with the tax of T per unit, and the quantity being exchanged being Q sub-tax, which is shown here, and that represents the tax revenue. So this is the summary, so to speak, of what we're going to do now. I thought I'll give you some visuals to just get you to warm up to this analysis. Now let's get back to the math. We have the equilibrium price, which is given by equating demand after tax with the supply. Now the demand is given by A minus, the demand function after tax is given by A minus B times P plus T, which is then equated to alpha plus beta times P. Then determines the equilibrium price P star, or we're just calling it P here. Now, basically equation 2 here, it implicitly defines the price P as a function of the unit tax. So what you're required to compute here is dP by dt. We want to understand how P changes with respect to T, and we're going to compute dP by dt by implicit differentiation. And then we're also going to see what the sign of dP by dt is going to be, and also see if there's any interpretation that this result lends itself to. Okay, so as I said in the beginning of the video, how do we go about using the method of implicit differentiation? We will differentiate both sides of the equation, which is equation 2, with respect to t. And once we differentiate that, we get, now see A is a constant, so minus b times dP by dt plus 1, we're differentiating with respect to t. And on the right hand side, you're going to get beta times dP by dt, right? Now let's just take this result to the next slide so that it's easier to interpret. Okay, so we have minus b times dP by dt plus 1, which is equal to beta times dP by dt. What I'm going to do here is that I've collected the terms containing dP by dt, put them on the left, so that we have b plus beta times dP by dt is equal to minus b, okay? Which then implies, when we solve for dP by dt, we get dP by dt as minus b divided by b plus beta. Now, if you remember, when I set up these equations for you in the beginning of this example, we said that b and beta are positive. So, if b and beta are positive, then clearly this shows that dP by dt is going to be negative, right? So, dP by dt is going to be negative, which is to say that the price, because P is the price at which the transaction is taking place, and this is the price which is going to be received by the producer. So the price received by the producer will go down. Since dP by dt is negative, the price received by the producer will go down if the tax rate increases. Also, if you notice here, the price received by the producer will not only go down, but it will go down by less than the increase in tax, because this is in absolute terms, it's going to be less than 1. So it goes down by less than the increase in the tax. Also, we can look at the price paid by the consumer, P plus T, and how that changes with respect to T. So, d of P plus T with respect to T is the derivative of P plus T with respect to T is dP by dt plus 1. And because dP by dt is minus b upon b plus beta, we add a 1 to it. So, that then gives us minus b plus, after taking the LCM, plus b plus beta divided by b plus beta, and you can see here that the b will, the minus p will cancel out the plus p, so that we get d of p plus t by dt as beta upon b plus beta. Again, that if you look at the sign of how the price paid by the consumer changes with respect to the tax, that is going to be positive. So, because beta and b are both positive, and at the same time dp plus t by dt is also going to be less than 1, because beta upon b plus beta will be less than 1, which is to say that the price which is paid by the consumer when the tax rate goes up, when t goes up, that is going to increase, but by less, again by less than the increase in the tax, which is also saying that the burden of the tax here, whether we look at dp by dt or d of p plus t by dt, that burden of the tax is going to be shared by both the producer and the consumer in this case, where the demand and the supply curves are respectively downward and upward sloping. So, to give you a visual sense of things, I have summarized this example so far with the following graph. You can see here that the demand curve before tax is this downward sloping line in blue. The original equilibrium, which shows the intersection with the red supply curve, the upward sloping supply curve, that equilibrium is given by the price P star. The equilibrium price is P star. Now, when the per unit tax is imposed on the consumer per unit of the good that he buys, that is going to create a wedge between the price paid by the consumer and the price received by the seller. So, you can see here the new equilibrium, it moves to P sub s. So, you can see here that the equilibrium price is now going to be lower, and that is what we were exactly saying, that the price received by the producer, which is represented by PS, the PS here, that falls when T goes up. And this is to say that there is some burden of the tax which is also going to be shared by the producer. Similarly, if you see here that the price paid by the consumer, that goes up, but again by less than the amount of the tax, because if you notice here, this vertical distance between the two demand curves, that represents T, and you can see here that the price paid by the consumer has gone up as compared to the before tax situation, but by less than the amount of the tax. So, to summarize, the price received by the seller plus the tax T, that is the price which is paid by the consumer, and this is to say that this tax is creating a wedge between the price received by the seller and the price paid by the consumer. Now, moving on, an alternative way to calculate dP by dt is also something that we can take into account. And here what we can do is the equilibrium condition that we had seen earlier, this A minus B times P plus T equal to alpha plus beta P. Now, instead of performing the implicit differentiation technique, we will simply just explicitly solve for P and then calculate dP by dt. So, that is another way of looking at things. In this framework, actually it is easier, because once you solve for P, you can see here, if I collect the terms containing P, I have B plus beta times P, which is equal to A minus alpha minus B times T. So, we have here that the equilibrium price is a function of T, and P is then given by A minus alpha minus B times T divided by B plus beta. So, that dP by dt is equal to minus B upon B plus beta. So, it is exactly the same answer that we got through implicit differentiation. And here it does perhaps look easier to first explicitly solve for P and then calculate dP by dt, but then things are not always this straightforward. And the whole point of implicit differentiation, if you go back to the previous video, which was introductory lecture on implicit differentiation. The whole point is that there are some situations where you can't explicitly solve for a particular variable as a function of another variable, as a differentiable function of another variable, and where you don't have explicitly defined functions, what implicit differentiation technique is telling us is that you can still go ahead and find the derivative of the function at a particular point. So that is why the technique is so useful and so powerful. Okay, let us look at the second part of this application. Now, and this is related to that area in pink that I showed you in the video a few minutes ago. So here you have tax revenue, and tax revenue is a function of T, the per unit tax. The question asks you, for what value of t? Now remember, because the question is on for what value of t does a quadratic function capital T reach its maximum. So small t here is your choice variable. So you'll be maximizing the tax revenue with respect to lowercase t, which is your unit tax. Okay, so for what value of t does a quadratic function capital T reach its maximum? So let's first find out the expression for the tax revenue. The tax revenue is given by small t times S, which is the quantity supplied in equilibrium after the tax. So here that will be t times alpha plus beta times P. You could very well use the demand function also, which is A plus B times plus T. You could very well use that, but the point is that this is a simpler expression, because the point is in equilibrium both will be the same. Alpha plus beta P would be equal to A minus B times P plus T. So we can use either, but this is simpler. So T times alpha plus beta P, where P is the equilibrium price. And now you can see here, when we do the calculation, capital T turns out to be the tax times alpha plus beta, and we can substitute for P here the equilibrium price which we had found, that is A minus alpha minus B times T divided by B plus beta. Let's open up the brackets. That then gives us alpha times T plus A times beta T. I'm just taking the T term inside. A times beta times T minus alpha beta times T minus B times beta times T squared divided by B plus beta. We can simplify this further by taking the LCM. So we have B plus beta in the denominator, and now once we cross multiply, we're going to get alpha times BT plus alpha beta times T plus alpha beta times T minus, A beta T minus alpha beta times T minus B times beta times T squared divided by B plus beta. You can see here that your two terms are getting cancelled. Alpha beta times T will cancel out this one, and what you're left with for as the expression for the tax revenue, that is then, you can see it's a quadratic function in T, and that is minus B beta times T squared divided by B plus beta plus alpha B plus A times beta, the whole thing multiplied by T divided by B plus beta. Now, because this is a quadratic function, basically this is the government seeks to maximize this tax revenue with respect to this little t. That so the government is choosing to the objective here is for the government to choose the tax rate which will maximize tax revenue. Now, if you know your maximization, you can straight away take the derivative with respect to t and put it equal to 0, get the stationary point, check for the second order condition. But if you are still not familiar with the calculus, you can use the results that we had developed for quadratic functions. And here you can see that, first of all, because the coefficient of t squared is negative, that then indicates that we have a max. Okay, we have a maximum at what point? The quadratic function will have its maximum at the point which is given by the coefficient of t divided by 2 times the coefficient of t squared with a negative sign in front. So minus the coefficient of t divided by 2 times the coefficient of t squared, and let's see what that turns out to be. So, the coefficient of t here is and because we have a minus in front, so it will be minus alpha b plus a times beta, right, divided by b plus beta, and that has to be divided by 2 times the coefficient of t squared. So, there is a negative here, so 2 times minus b beta, that will come in the denominator here, and the b plus beta term will go to the numerator. So, with that we can now simplify further. You can see that the b plus beta terms will get cancelled, and now we have that the quadratic function will have its maximum at alpha b plus a times beta divided by 2 times b beta. Okay. We will now look at the last part of this particular application on taxes. Generalize the foregoing model by assuming that the demand function is f of p plus t and the supply function is g of p, where f and g are differentiable functions with f prime negative. So, that is to say that you have a demand curve which is downward sloping, and because g prime is positive, the first derivative is positive here. So, we have a supply curve that is upward sloping. The equilibrium condition is given by f of p plus t. The equilibrium price is obtained by equating f of p plus t to g of p, and this equation defines, and let us assume that it defines p implicitly as a differentiable function of t. Okay. So, if this equation defines p implicitly as a differentiable function of t, then find an expression for dp by dt by implicit differentiation. So, this is just generalizing what we have done so far with the linear demand and supply functions, but this is more powerful because it's a more general setup. And you can see here that the equilibrium condition, when we differentiate both sides of the equation, we get f prime of p plus t times dp by dt plus 1 is equal to g prime of p dp by dt. Collecting the terms containing dp by dt and bringing them to the left, we have f prime minus g prime, right, times dp by dt is equal to minus f prime of p plus t, which then implies that dp by dt is equal to minus f prime divided by f prime minus g prime. Now, let us see what will be the sign of dp by dt here, and let us see if we get the same result that we did for the linear demand and supply functions. And yes, indeed, the result is the same, because see, look here, f prime is going to be negative, so the numerator, the whole numerator becomes positive, right? And the denominator, f prime is negative and g prime is positive, so you are basically adding two negative numbers, and therefore the denominator will be negative. So, the whole thing is going to be negative. Right, and let's now look at what will be, how will the price paid by the consumer change with respect to t. So, the derivative of p plus t with respect to t is equal to dp by dt plus 1, and here you can substitute for dp by dt, which is minus f prime, right, divided by f prime minus g prime, which we derived in the previous slide, plus 1, and that then can be written as, if I just remove the minus f prime, right, this can be, and if I take the LCM, then in the numerator I will get g prime, right, g prime, and in the denominator I will have g prime minus f prime. So, whichever way you want to write it. If you take the LCM, you will get minus f prime plus f prime minus g prime, but the f prime terms will get cancelled and you will get a minus g prime, but there is f prime minus g prime in the denominator, so you can just change the minus signs to get this particular result. And here also you can see that the price which is paid by the consumer, that increases when t goes up, but it increases by less than the amount of the tax. So, this is just to generalize and summarize the whole application that we had done with the linear demand and supply functions, and with this we conclude the first part of this lecture. Thank you.